All right, this is AP, AB, and BC Calculus. We're doing Unit 7, Section 1, which is modeling situations with differential equations. So let's get started. All right, so differential equations are equations that involve one or more derivatives. So here are some examples. dy dx equals 2x plus 3. 3y prime plus 5y double prime equals 7. Dy dx equals x squared over y. So that's just a few examples. It doesn't have to be y and x. It could be dy, dt, etc. In this section, we'll focus on translating word problems into differential equations. We'll learn to solve them later. For now, it's imperative that you can correctly construct a differential equation from a word problem. You'll often hear differential equations called diff-EQs, but it sounds like diff-EQs. In college, after Calc 1, which is basically AB Calc, and Calc 2, which is BC Calc, and Calc 3, which is multivariate in most schools, there's often a course specifically on ordinary and partial diff-EQs. All right, so let's walk through some key phrases. So the rate of change of blank with respect to time means d blank dt, right? So for instance, the rate of change of y with respect to time would be dy dt, right? The rate of change of area with respect to time might be dA dt, right? And so on. The rate of change of blank with no mention of with respect to what variable is also generally t, right? Or whatever other independent variable is mentioned in the problem. So if you just hear the rate of change of y, it probably means dy dt. But if you know that x is the variable in the problem, not t, then it would be dy dx. So again, if there's no mention, and instead of time, right? So instead of time here, let's say it said something like the rate of change of the area with respect to the radius, right? If you saw that, it would be dA dr, right? Rate of change of area with respect to time, or with respect to radius, rather, right? So there's different ways to see this, but that's the idea. So when you hear the phrase is directly proportional to, that means is a constant multiple of something, right? So if you hear is directly proportional to, let's say, x, it would mean is equal to kx. If you hear is inversely proportional to, it means it's the constant divided by that thing, right? So for example, and we saw this in Algebra 2 and Pre-Calc, right, multiple times, but if I say something like the rate of change of b is directly proportional to b, well, that would mean dB, probably dt, right, unless we're given a variable, is a multiple of b. So dB dt equals kb, right? If I had, instead of saying directly, if I had said inversely, then it wouldn't be k times b, it would be k over b, right? So that's just the idea that we want to be able to translate these phrases into an equation. The is in the statement is generally the equal sign in the equation. So here's a couple of examples. The rate of change of the number of people p is proportional to the time t. Well, that would be dp dt, right? Because that's the rate of change of the number of people p, right? So that's dp dt, right? And then is proportional to t, well, that's this k times t. The rate of change of y with respect to x, well, that's going to be dy dx, right? Is inversely proportional to the square of y. Well, that means k over y squared, right? The y squared's on the bottom. So that's kind of the idea of what we're going to be doing in this section. It's a lot of translating phrases into mathematical equations that involve derivatives, right? And that's what we call a differential equation. So given the word problem, we're going to write the corresponding differential equation. That's it. We're not solving anything. We're just writing it. So the rate of change of the population is directly proportional to the square of the population. So we're going to go ahead and say dp dt, because in general we default to it being time unless we're told otherwise, right? Is directly proportional to the square of the population. Well, that's going to mean k times p squared, right? Because that's the square of the population. The rate of change of w is directly proportional to the cube root of time t. Well, that's going to be rate of change of w is going to be dw dt, because here they did tell us the time, right? And it is directly proportional, so k times the cube root of the time t. And k is a constant, right? We're going to find k later when we learn how to solve things. The rate of change of height is proportional, so height is h, is proportional to the reciprocal of the cube of the height, right? So rate of change of height is going to be dh dt, because it's how h is changing with respect to time. And it is proportional, meaning k, times the reciprocal of the cube of the height. Well, that would be 1 over h cubed, right? And you could either write it this way, or you could write it as k over h cubed, right? Now, interestingly enough, there's another way to write this phrase, right? And I should probably bother to write the dHdt just to be clear, because it was on the other end, but in case when I box this answer, that would be fine too. So you could also say, the rate of change of the height is inversely proportional to the cube of h, right? And you can see that because notice that I said proportional to the reciprocal. Well, that would be 1 over h cubed. So this is another way to write that, right? Same idea, different way to write it. The rate of change of the volume v is inversely proportional to time t. Well, rate of change of the volume is going to be dv dt. Inversely proportional means that this thing goes on the bottom, so k over t, right? And k is a constant. So there are a couple common types of growth that we see in differential equations. So one of them is linear growth. As you'll recall from algebra, linear functions or lines have a constant slope, thus a constant derivative. So if you see dy dx equals some k, where k is just a constant, that represents linear growth, right? Another common type of growth is exponential growth. This one's really common in growth modeling, and you should get used to seeing it. One that you'll learn when you get to BC Calc is logistic growth, but we're not going to mention that here because we don't really touch on it in AB. We'll have a section specifically for logistic growth in this particular chapter or in this unit for the BC students, and that'll be Unit 7, Section 9 for BC only. So exponential growth is really common. The phrase you're going to hear associated with it is the rate of change of a thing is directly proportional to the thing. So for example, the rate of change of y is directly proportional to y, right? And you'll see that I did it here with an x instead of a t, but it's the same idea, right? So the rate of change of a thing is directly proportional to the thing, right? That's exponential growth. So we're going to spend more time on that later. We're going to do an entire particular section on it. If k is greater than 0, we're looking at what's called exponential growth. If k is less than 0, we're working on what's called exponential decay, and we'll spend some time talking about that later. So which of the following equations represents linear growth? And we're going to choose all the ones that apply. So remember, what it means to be linear growth, right, is a rate of change, or whatever the rate of change is, so it doesn't have to be dy dx, equals some constant. That's what it means to be linear growth. So this one is linear, right, because it's the rate of change equals a constant, right? This one is not, because it's not a constant. This one is linear, and this one is not, right? So again, we're looking for, because this number is a constant slope, right? Constant slope. And it doesn't have to be dy dx, it could be dy dt, it could be dA dt, it could be dq dx, it doesn't really matter, right? All right, and then one last example in this video. So for practice, which of these differential equations is exponential growth, right? So remember, exponential growth is d something, d, let's say t or x, it doesn't matter, equals k times the something, right? So the rate of change of a thing equals k times the thing. So dy dt equals 5t is not exponential. Dy dx equals 3y is exponential. Dy dt equals 1/5 y is exponential, right? Because it's the rate of change of y is some multiple of y, right? And this one is not exponential, right? So again, it's the rate of change of a thing equals some constant times the thing. That's how we get exponential growth, okay? And that is it for Unit 7, Section 1.